With an introduction like that, I'm really in trouble because you're ratcheting up expectations. Let's see. So what I wanted to bring people up to date on was what is going on in trying to expand the ground-based network of advanced gravitational wave detectors. What I was going to talk about here is to show a bunch of slides first for people who are unfamiliar with LIGO and advanced LIGO. But looking at this audience, I'm going to skip through all of those, which will save us some time. So what I really want to do is talk to you about some of the goals for this so-called Global Gravitational Wave Telescope, tell you about the status of the development of these advanced instruments, not just advanced LIGO, but in Europe, and most of the talk will be about LIGO Australia, and then something about what's going on in Japan and India. So there'll be some, but not a lot of science in this talk. There'll be a lot of politics and a lot of current events. So I'm warning you ahead of time. So it's mostly more of a cultural talk than anything. So I'm going to skip through things that you've already seen, I'm sure all of you have seen, and we're going to build a bunch of these. That's the first part of the talk. So let me start here. And of course, you've all seen this. You know that LIGO has two sites, one in the state of Washington, two observatory sites, and one in Louisiana, with in Louisiana 1 4-kilometer instrument now, or pieces of a 4-kilometer instrument, and in Washington a 4-kilometer and a 2-kilometer. This was initial LIGO. These instruments are being taken apart now. You can find parts in dumpsters and various people's offices in those two places. But the thing I want to emphasize in this slide is that the two LIGO sites are about 3,000 kilometers apart. And the important thing is that that's not too far apart, given what I'm going to talk about for the rest of the talk. And so when we think about an observatory with nodes around the globe on a sort of continental and global scale, these two sites are relatively close together. So just a little bit about where we are with LIGO. It's probably about 3 or 4 slides. In 2005, LIGO reached its design sensitivity. These instruments can now measure differential arm lengths at an interferometer to the order of 10 to the minus 18th meters. We had a first science run at full sensitivity in 2005 to 2007. This is a plot most of you have seen, but what it does try to illustrate is the yellow line is the science requirement document prediction of LIGO sensitivity from 1995 or so, and the two other curves show the sensitivity at the two observatories for the 4-kilometer instruments. And it just gives you a sense of the frequency band where LIGO is sensitive. It's something like 40 hertz up to several kilohertz. Okay, this run got lots of good data. We published a bunch of papers. Some actually have some astrophysical significance. As everybody knows, we haven't observed a gravitational wave in the S5 run. We weren't surprised because the expected rates, which do have errors in the exponent, led us to expect a few % per year probability of seeing something. So this run is behind us. We then had another science run we called S6 with what we called enhanced LIGO, which was some modest upgrades to LIGO, but mainly using some of the technology and prototypes that are key to advanced LIGO, inter-real interferometer, inter-real science run. And that run ended this past October. And again, you can see the sensitivity curves down there. The black curve is initial LIGO, the purple one is enhanced LIGO, and you can see the improved sensitivity in the shot noise dominated region, the high frequency region. So this run was a big success. We're still analyzing the data. And so that then lets us move on to advanced LIGO. And so this is the sort of PR slide for advanced LIGO. But the important thing about advanced LIGO, as you can see from the plot, is that the goal of advanced LIGO is to improve the sensitivity by about a factor of 10. Since for extragalactic sources, we sort of see the first order like the volume, that will increase the rate by a factor of 1,000 to the point where instead of having a few % or so probability of seeing events per year, we will see, tens, more, less, but something like that numbers of events per year. We certainly hope. But the other thing advanced LIGO will do is reduce the low frequency limit where we can see we're sensitive to a reasonable signal from about 40 hertz down to about 10 hertz. And so that's a region where there are more pulsars to be seen. There's better sensitivity to remnant gravitational waves from the Big Bang. We can see higher mass black hole in spirals and so on. So there's more observational possibilities as we pull the lower limit on the frequency band down. So advanced LIGO is our big deal. I just point out here in red that if it works well, 1 day of observing with advanced LIGO is equivalent to more than a year with initial LIGO. So getting on to advanced LIGO is what we've been about for several years now, and it's going on now. So the status of advanced LIGO is that it's fully funded. It's about $200 million from the NSF. There are major contributions also from the UK, Germany, and Australia. This is funding 3 4-kilometer instruments, 2 at Hanford, and it's in red because this becomes relevant for LIGO Australia, and 1 in Livingston in Louisiana. We're about halfway through construction now. Construction's been going on for 3 years. Many components have been fabricated and are being fabricated. We terminated our observing run last October, and at that point we started sort of pulling out, decommissioning initial LIGO and enhanced LIGO, and we're now installing advanced LIGO. So the project is on schedule, it's doing well within its budget, and the last bullet is the important one. If all goes well, we hope to take, I should say hope instead of expect, to undertake the initial science runs with the first 2 of the advanced LIGO instruments somewhere in the 2014-15 timeframe. If the project goes ahead the way it's scoped with 2 instruments at Hanford, the 3rd one maybe in 2015. And that will be the beginning of a cycle where we gradually, as we did with initial LIGO, but more quickly we hope, bring the instruments to the design sensitivity. So there'll be interleave science runs and what we'd call engineering runs where we try to understand what's wrong with sources of noise and fix things, and then go back to science runs. So that will be a process that will take, it won't be instant, it'll take a couple of years, we hope. Okay, so now let's move on though from advanced LIGO to the bigger picture, and that is this question of trying to develop the capabilities to do gravitational wave astronomy. And of course that's the purpose of advanced LIGO, that's what the PR slide said, but as you'll see, and it's probably clear, with just instruments at the 2 LIGO sites, that you can't do that. You need more to be able to point out sources on the sky and to get other information. And so the rest of this talk is about what we're trying to do to make that happen. And so what we really need is, as it says here, is a global array of these advanced detectors that are equivalent to advanced LIGO, separated by continental distances. And that's why I say 2 in the US is too small a separation. So we can triangulate the gravitational wave sources on the sky. And the way the triangulation works is we measure the time of arrival of a signal at a number of these nodes in an array, and that time difference helps us point into the sky. And so later on you'll see some plots about how accurately we can do that under different assumptions. So let's see. Okay, so this is just a bit about that. Excuse me. So as you of course all know, in addition to advanced LIGO, or LIGO, there is Virgo in Italy, and Virgo is building advanced Virgo, and I'll say something about that in a while. So in some sense, we have had with Virgo and LIGO, and will have, a triangle of 3 instruments, 2 sites for LIGO and 1 in Italy. And what you'll see, of course, is that if you try to point to a source in the sky with 3 sites, the pointing accuracy is relatively good, comparatively speaking, if that source is perpendicular to the plane of the triangle. If it's in the plane of the triangle, the resolution is really crummy. So in some sense, what you'd like to have is a buckyball of detectors surrounding the globe, or if you can't afford that, at least a tetrahedron, sort of the first order of triangle pointing in all directions, so that all sources are approximately perpendicular to 3 of the instruments, and you can get good resolution. The other benefit of doing this kind of thing is that, as you know, gravitational waves have 2 polarizations, and detectors oriented at some angle with respect to each other allow you to project out the 2 polarizations and determine the polarization of the source. And the LIGO instruments are aligned together for reasons that are go back in history and to optimize discovery possibility. So with new and additional instruments, there's the possibility of orienting these instruments at angles with respect to each other and being able to gather up this polarization information. In the context of this kind of global network, of course, we want to view all the instruments that will exist, or we hope will exist, as somehow a single array, and to analyze all the data together in a what's the word? As sort of data from one instrument. So let's see. I probably said all this. Okay, so let me tell you where we are and where we're going, because that's the meat of this talk. First of all, in the last few years, there's the beginning of this putting together of a global network. The two LIGO observatories, Virgo in Italy and the GEO instrument in Germany, have all been working together. The GEO collaboration is part of LIGO. LIGO and Virgo have been working together to analyze our data as if there were a single array. We do coherent analysis with all these detectors. And so this is sort of the beginning of this array. We've put together an agreement with Virgo that's being renegotiated now, but that agreement that was signed 3 or 4 years ago made it very clear that the collaboration between these two, the meta-collaboration between these two collaborations will be open to other interferometers when they reach the appropriate design sensitivity. This is a message to the rest of the world that when you have advanced instruments, we want you to join into this data sharing arrangement. So this is where we are now. In the future, what we hope will happen, and this is what the rest of the talk will point to, is that we will have a global network with advanced instruments at the two LIGO sites, in the US, of course, in Europe, having advanced Virgo, an instrument in Japan, and an instrument in Australia. And so I want to try to motivate all this. So here's a picture of, this is an approximate tetrahedron, and so you can see the European sites, Virgo and GEO, the node in the southern hemisphere in Australia, a node in Japan, and the two LIGO sites. So this is in some sense the goal. So I want to tell you about the status of some of these things now. Okay, we told you about advanced LIGO. Advanced Virgo will have 3-kilometer arms. Advanced Virgo is designed to aim at the same sensitivity approximately as advanced LIGO, so it'll be in some sense matching. It may actually have somewhat better sensitivity at lower frequencies. Advanced Virgo is funded by the funding agencies in France and in Italy, and the goal of Advanced Virgo is to be online at about the same time Advanced LIGO is online, 2014, 15 or so. And the second bullet you've heard before. So Advanced Virgo is funded. It's in construction now. The funding is coming a little more slowly than the proponents had hoped, but it's going and it's going to happen. So that node in the advanced detector array looks like it is in good shape. This whole question of this global array has been, of course, floating around for a long time, and one of the instruments in the field is a committee, an international committee called GWIC, the Gravitational Wave International Committee. And several years ago, to try to look ahead to where the field was going, GWIC put together a committee to write a strategic roadmap for the field, looking over 30 years, looking at where the field is going on the ground and in space. And the part of it that looked at the future of the ground-based aspect of the field pointed out that that gravitational wave astronomy needs this global network that would be anchored by advanced LIGO and advanced Virgo. But the key was an instrument of comparable sensitivity in the southern hemisphere. And this strategic roadmap for the field pointed out that this instrument would be the highest priority for ground-based gravitational wave science. And it pointed out that within the southern hemisphere, Australia is the best site for a number of reasons that I'll get to. So this is something that helped motivate the field, helped motivate a number of us to think about what we could do to make this happen. So there's this so-called LIGO Australia, which is an idea now. It doesn't exist yet. We hope it will. And the way it came about is very simple. It was a question to ask yourself. Think about being 4 or 5 years from now and ask yourself scientifically which is preferable. to have, from advanced LIGO, 1 instrument in Livingston and 2 at Hanford, as is the canonical plan for advanced LIGO, or to have 1 instrument in Livingston, 1 in Hanford, and 1 in Australia, so that there is a Southern Hemisphere instrument equivalent to advanced LIGO. And of course, that's the scientific no-brainer. And this question is really the origin of the idea of LIGO Australia. And so this is just a way of trying to motivate the fact that it is a no-brainer. This is a calculation that's somewhat old now, but it shows the sort of pointing accuracy on the sky for an in-spiraling neutron-star pair with a signal-to-noise of 8. And the plot, let's see, over here, I can't tell left from right. This is the plot you'd get with just advanced LIGO and advanced Virgo. And the plot on the other side shows what happens if you take one of the 2 instruments at Hanford and Washington and move it to Australia. And of course, the improvement is striking. But there'll be some more details later in the talk. And in fact, it seems straightforward, but we really, to try to motivate this idea and bring around the people who had to support it and have to support it, we wanted to ask ourselves, more detailed questions. And so the LIGO Scientific Collaboration formed a committee that Ray Weiss chaired, and we asked them to perform an evaluation of the scientific benefits of doing this, looking at pointing resolution and things of that sort, and whether there were any downsides. The bottom line for that, and I'll show you some of their calculations, was that, and I'm going to use abbreviations like that throughout some of these slides. So AHLV stands for Australia, Hanford, Livingston, Virgo. HHLV is the canonical advanced LIGO, 2 at Hanford, 1 in Livingston, 1 in Virgo. So that committee concluded that the benefits scientifically are substantial, that the pointing accuracy is improved by something like a factor of 5 or 10 over much of the sky, and you'll see some details in a minute. And they couldn't find any real disadvantage in having an Australian detector instead of 2 at Hanford. Any of the flexibilities of having 3 detectors will happen wherever they're located. There didn't seem to be real advantages about having co-located instruments at one site. There would be if there were no common noise and coupling between the 2, but that doesn't seem to be the case. So this committee was very encouraging, and these are some of the slides that they produced. So this, can I even read this? So this is a plot which shows the average angular error on the sky for what they call an unmodeled source, sort of a burst. This is not an in-spiral where you know the waveform, but just a GRB or whatever it is. And so the top plot shows the median angular error, and that is for the array with 2 instruments at Hanford, 1 at Livingston, and 1 in Virgo. And you see from the color coding there, over most of the sky, the pointing error is the order of 10 degrees. If you instead move one of the instruments from Hanford to Australia, you get the bottom slide, and there you see there's lots of area where the color is more purple-blue, which is in the few degree range for the error. They also did some calculations to try to look at the pointing accuracy for neutron star binaries, where you know what the waveform looks like. And so here again is the comparison between HHLV, 2 at Hanford, Livingston, and Virgo, and moving 1 to Australia. And so what you see on the right-hand side, first of all, is this dot is where the source actually was, in right ascension and declination. First of all, you can see there's sort of a twofold ambiguity as to where you can reconstruct the source, but also you can see the large error. And I want you to just notice the difference in scale between the right and left. The other panel shows what happens if you move one of the instruments to Australia. You can see the actual point of the source right in the middle of that colored blob. And if you look at the right ascension scale, it's about a factor of 10 smaller or more. And the same with the vertical scale. So the ability to point a source, a model source like this, gets, obviously much, much better. This is a way of looking at this pointing accuracy. The vertical scale is the fraction of 4 pi, around the sky. The horizontal scale is the pointing accuracy in square degrees. And so the red curve, and so this is the distribution integrated over the sky. And the red curve shows the sort of canonical advanced LIGO situation with 2 instruments at Hanford. And you can see, well, you can read the numbers, but again, it's the order, the numbers are the order of 10 squared degrees. If you move an instrument to Australia, you get the blue curve. And you can see that for much of the sky, you're talking of a few square degrees. So this is the motivation. But in addition, there are other things you can learn. For example, one of the important things for neutron star binaries is to try to understand the orientation of the binary with respect to the observer, because these things are, in a sense, standard. I call them standard sirens, but we know their luminosity in gravitational waves. So if you know the orientation, you can use them as standard candles, if you will. So this shows that orientation with respect to the observer with 2 instruments at Hanford and 1 in Australia. And again, you can see the sort of twofold ambiguity without an Australian site. That ambiguity collapses if you move something to Australia, and the accuracy is much better. So that's the motivation for LIGO Australia. The concept is very simple, and that is it would be a direct partnership between LIGO Laboratory and Australia to build an Australian interferometer. And the site would be in Gingin, which is in Western Australia. It turns out that's geographically almost an ideal site. Somebody told me that if you asked where the perfect site would be in the southern hemisphere, given LIGO and Virgo and Japan, it would be about 300 miles off the west coast of Australia. So on a global scale, that's nothing. So it's a good site geologically, and there's already a gravitational wave R&D facility there. There's an 80-meter interferometer. So the site is clear. As part of this arrangement, LIGO Lab, with our partners in the UK and Germany and Australia, would provide all the components for one advanced LIGO interferometer, one of the 2 that would go to Hanford. What I jokingly say, we would package that stuff up as a Heath kit, send it to Australia. The Australians have to provide the housing for it. And what they would provide is the infrastructure, which is absolutely non-trivial. It's roads, it's buildings, it's a very expensive vacuum system. You know, this vacuum system for these interferometers have these 4-kilometer arms. The diameter of the vacuum tubes are 4 feet or so. So it's a massive vacuum system. If all this happens, this interferometer in Australia would be operated as part of LIGO. And so it would really be part of the LIGO network. And so its operations would be coordinated with the LIGO instruments in the US. The data would be part of the LIGO data set and so on. It would really be a third LIGO instrument. Just to give you a flavor of what the Australians would have to provide, because it's non-trivial, you can see a picture of one of the LIGO sites, the vacuum system buildings, the close-up of the vacuum system on the right. And some of the vacuum tanks where the 2 arms come together. If I stand next to those vacuum tanks, I'm 6 feet tall, I go about 2/3 of the way up. So it's massive stuff, and it's very expensive, and of course that's one of the issues. So this Australian site at Gingin, there's a picture there of the way it looks now, is about 80 kilometers north of Perth. It's about 15 kilometers from Great Beaches, so that's appealing to some of us. It's important that Australia has a very strong gravitational wave community, so they could actually pull this off. And there have been many Australians who have been and are part of the LIGO scientific collaboration, something like 50. So there's a core of scientific and technical expertise in Australia that can do this. But, and it's an important but, the economy in Australia is about 1/15 of the US economy. And so the funding that is needed, and it's a big number you'll see soon, in Australia it's, say, very challenging is understating it. The construction cost on the Australian side, if we do LIGO Australia, is something like 150 million Australian dollars. And the exchange rate is about 1-to-1. If I scale that by the economy, 15 times 150 million is multi-billion dollars. So I just want to say that so you realize, if you think about the US, how difficult it would be to find that kind of money. And that's the real challenge in Australia. One of the things we wanted to do very early on in discussing this with our colleagues in Australia was to sort of write down the rules of the game. So we put together a list of what we call requirements, but it's really a set of things that we would want to be part of the relationship with Australia to assure that if this happens, the instruments work well, they're designed well, they're operated effectively, they're operated as part of the network, and so on. So I've got a few slides that come from this lengthy document that went back and forth. But the first one really says is that it's political, and that is we want to have an agreement between the US and Australia only. We want to have a two-nation agreement. That doesn't mean other countries can't get involved, but we don't want to try to negotiate 3- or 4-fold agreements. And so the arrangement is that if other countries want to get involved, and you'll see later that India has some interest, they would sort of team with Australia. But the overarching agreements would be between the two nations. The proposed facility will be managed jointly by the US and Australia as an integrated part of LIGO, which is, of course, very important. Australia will pay for the cost of relocating and installing the Heath kit, establishing the site, and importantly, they would be fully responsible for operating LIGO Australia for at least 10 years. And in the end, of course, to skip a little bit ahead, LIGO, as you know, was funded by the National Science Foundation. And we had to set up conditions which would, in the end, be acceptable to the NSF if all of this goes ahead. And one of the things the NSF would not have wanted is to have some sense of mortgage to support operations of this facility outside the US. So we made it very clear at the beginning that this would be an Australian responsibility. And here's one of the, not one of the sticking points, one of the unfortunate things, and that is for this to happen, we need a commitment from Australia by this coming October. And the reason is that LIGO Australia would be a diversion from the canonical Advanced LIGO project, which the US Congress signed off on and says there are going to be 2 interferometers at Hanford. And if we want to take that diversion, that has to happen by this fall or this coming new year. Otherwise, these components for the second interferometer at Hanford have to be installed at Hanford. So we don't have a lot of time, and this, as you'll see, is one of the big difficulties. So anyway, there are just, as I say, pages of detailed requirements, but I'll just mention a few because it'll give you a feeling for the fact that we've tried to think some of these things through in some detail. So if this happens, LIGO would need to approve any technical changes or modifications. So we make sure the instrument will be a good match to the other advanced LIGO instruments. People from Australia would come to the US and help us commission advanced LIGO, so they would learn about its problems, learn about its idiosyncrasies, and get some training. This just says that the facility would be operating as a third part of LIGO. We would have the ability to concur with key staff there just to make sure that we're comfortable with the key people who would be involved in this, the director, people who'd lead the construction, and so on. So there's a whole list of these things. So let me tell you now about where things stand. And there's 2 sets of slides here. What's going on the US side and what's going on in Australia. And so the time scale for all of this was that this whole idea came about in October 2009, so about a year and a half ago. And excuse me. The first time we sort of surfaced this in some kind of official capacity was an informal talk to an NSF review of advanced LIGO just about a year ago. And that committee, a committee was not asked to look at this, but we sort of gave them a lunchtime talk. And in their report, they strongly endorsed this idea and said it was a scientific no-brainer. They really thought NSF should seriously look into doing LIGO Australia from their side. Following that, we put together a very thick white paper telling about the science, how this should be managed, the risks, and all these kinds of things you do to have a document to convince a funding agency, convince colleagues that this is a sensible thing to do, it's important scientifically, and it's not going to screw up other things. And so that was less than a year ago, and NSF, following up that recommendation from the Advanced LIGO Review, got on board about not necessarily doing LIGO Australia, but on taking it seriously. And so they put together a strong team to review LIGO Australia June last year. And at that review, we presented the white paper outlining all of this good stuff. Part of that white paper was the scientific case that was put together by Ray Weiss's committee. We had some key Australians attending there to show their support, to be able to answer questions about the Australian side. And so it was a very in-depth review. It was very successful. I mean, the review panel, it says here, strongly endorsed the concept, said the practical issues were well understood, the science gain is well worth the risk. All the good things we wanted. The thing we found out right after the review was that several of the key NSF officials who would have to support this were really skeptical about advanced LIGO. They were really nervous about doing anything to perturb it. I mean, LIGO Australia. They were nervous about doing anything to perturb advanced LIGO. They came into the reviews very skeptical, and as a result of this review process, they turned around completely. They became convinced this was a really important thing to do, and they became very strong supporters. So it was a really successful review. So the NSF, as we know, the NSF got on board, but the next step was the National Science Board. And for this to happen, the National Science Board would have to be comfortable with it. So last August, the NSF presented this to the National Science Board as a sort of information item. There were no objections, so that was taken as de facto approval. And so after the Science Board meeting last August, we got a letter from the NSF essentially saying, you can proceed with this, which meant that they were willing to have us divert one of these advanced LIGO instruments to Australia and go ahead with this arrangement if, and the quotes are here, Australia financial management and oversight conditions in LIGO Lab's requirements document, that stuff I told you about earlier, are met by next October. So this was in some sense the end of the story on the US side. We had gotten to the point I think this was September, when everything on the US side was put in place to make it happen. If our partners in Australia could come up with what they needed, which understandably is more difficult. They needed to come up with lots of money. We weren't looking for money. So let me tell you about where things stand on the Australia side. First of all, as time has gone on and more people have learned about this, it's really been recognized by many people as a real opportunity for Australia to get in on the ground floor of gravitational wave astronomy. As a result, 5 of the leading Australian research universities have sort of banded together at the level of their vice presidents for research to do what they can to make it happen. And so there's a sort of management entity, a center being set up at the University of Western Australia, which is the university closest to the Gingin site. The universities have been seriously discussing how they can contribute to the operating funds, because that's finding that kind of money is also difficult. And for example, the University of Western Australia has talked about contributing $5 million should all this happen. A proposal has been put together, a very nice proposal. I'll show you just the cover page in a minute, by these universities. It's a proposal to construct LIGO Australia. It requests 140 million Australian dollars. And that proposal, a week or two ago, was completed and has been now sent to government officials, including the Minister of Science. So this is the cover page of the proposal. It says LIGO Australia on the crest of the wave, and you notice the map. I think it's good for all of us to recognize there are 2 ways of looking at the world. And so there's a tetrahedron upside down from the way I showed it before. The 5 universities, this is the second page of the proposal. The 5 universities involved are the University of Western Australia, Australian National University, the University of Adelaide, Monash University, and the University of Melbourne. And at the bottom, you see it says further information, please contact, and I want to point out the name at the right, Stan Whitcomb, who's been working very hard on trying to make this happen, has been appointed the acting director. And so Stan has been the one who's been trying to glue together the U.S. and Australia, trying to find ways of trying to help the Australians succeed in finding the resources to make this happen. So let me just tell you a little bit more about where things stand. That proposal has a cost estimate. We wanted to make sure that cost estimate was right. It would be very bad to get money from Australia and it not be the right amount of money and have this whole thing get into trouble. So we used the advanced LIGO cost estimates for some things. We used the initial LIGO cost estimates for things like the buildings and the vacuum system and so on to try to vet what the Australians have done and be comfortable that the number is right, and we are. I guess I've told you the rest of this. We, mostly being Stan and our Australian colleagues, have talked to a lot of people in Australia, scientific people, astronomers, academic colleagues. There have been conversations with business people, industry people, to try to understand the right ways of going about getting this funded in Australia. Of course, one of the things in Australia that's very relevant is the square kilometre array is the #1 priority for Australians. Astronomy. Astronomy is very important in Australia. And so if LIGO Australia is to happen, first of all, it can't be seen as a threat to SKA. And more importantly, if there's some kind of synergy between SKA and LIGO Australia, that's very important, and that will be a big plus. We've generated a lot of good publicity. Just some articles. There's one from Science. Here, there's an Australian science magazine called Cosmos up there, Physics Today, one of the American Physical Society publications, trying to get the word out, trying to interest people and excite them about this. So let me get back to money in Australia. So as I said, the need for constructing it is $140 million. The need for operating it is about $6 million a year for 10 years. So that's $200 million, which, as I said earlier, is a lot of money for most places, but including Australia. It turns out there's not now an established process to fund such a costly science project in Australia. You know, in the U.S., there are agencies you can go to. They have procedures to handle things of this scale and evaluate it and go to Congress. That doesn't exist in Australia. So if this is going to happen, and happen in the short time we have available, it's got to be done through the political route. And I'm just to illustrate it very glibly, that's what the other bullet is. The political route means having the science minister say, let's do it, and convincing other cabinet members to do this. It's not going to happen unless at the very highest levels in the Australian government people want to do this and make it happen. So there's been lots of talking to people in government, lots of talking to people in their funding agencies. The proposal was submitted, among other people, to the science minister. There is the possibility that next week the vice chancellor of the University of Western Australia may meet with the science minister. We hope that happens. We'll see what the reaction is if it happens. So this is the kind of thing that is being done now to try to seek this kind of funding, which is outside of the mainstream of how things are done in Australia. And so, of course, as a result, you know, the odds are not great. And so I think this is my last slide on that, and that is we are trying hard. We have till this fall to make something happen. The science funding now in Australia, the climate is very poor. I mean, the whole world has gone through a recession. We've even heard rumors that there are talks about large cuts in funding next year for medical research in Australia. And so this gives you a flavor for how challenging this might be. So the bottom line of LIGO Australia, which I think is, you know, something that's just got to happen scientifically at some point. And we've made a lot of progress, obviously. We've got the NSF on board. We've got supporters in Australia. There's a proposal and so on. But it's still a really big challenge if we're going to get this Australian funding committed by this fall. We don't need the funding by this fall, but we need some message that's strong enough for the NSF to tell us and agree that we should not install the second interferometer at Hanford. And so that's the big challenge. That's the scary thing right now. And I really have to say that at this point, politics, and I'll show you what I mean in a second, and nature are not really well aligned with our goal. And this is about politics and nature. There was an election in Australia last summer, and it was almost a tie in their parliament. And so the ruling party isn't very strong. There are a few people who have a lot of leverage now, so that's one of the problems. But the other is that Australia has had their share of natural disasters the last few months. There was massive flooding in Queensland. There was a huge hurricane. And so they have economic problems. They have natural disasters to cope with. We're trying to get a lot of money, much more than they're used to thinking about for a science project. So we are, I guess this says it, it's the last bullet is it's a long shot, but we're working hard to do this. So the summary of LIGO Australia is, LIGO Lab has offered to locate the third interferometer in Australia. NSF has approved it, subject to Australia providing the vacuum system, the site, the buildings, to operating the interferometer, the funds and people to install it, and the funds and people to operate it for 10 years. We have some small number of months left. It turns out if we get to the point where we get a signal from Australia that if you give us a few more months, maybe something will happen, we could probably do that, but it's really tight. So it's a long shot, but we really still hope it'll happen. So that's LIGO Australia. There are things going on also in Japan and India that I want to tell you about that are relevant to all this. Excuse me. So let me start with Japan. In Japan, for a number of years now, there have been proposals to build advanced gravitational wave interferometer called LCGT, the Large Cryogenic Gravitational Wave Telescope. These proposals for 3 or 4 years have not been funded. LCGT, as you can see from its name, is cryogenic. It would be underground in the Kamioka mine. By cryogenic to try to reduce the effect of thermal noise on the sensitivity of the instrument. It would be underground to try to reduce the sort of seismic impact, the rumbling of the earth that moves things around. So for several years, this has been proposed, been turned down, or the proposal hasn't gotten far in the process. All of a sudden, last June, LCGT received about $100 million for the next 3 years to begin the construction. And I think it surprised everybody. It was part of, the U.S. analogy is stimulus money. It was a great thing for the field. That money did not include the money it would take to drill the tunnels for the instrument in the Kamioka mine. That money was expected to come in the Japanese fiscal year that starts at the end of this week, about $60 million. And so the plan in using this $100 million was to develop LCGT in 2 phases. The first phase would be sort of almost a stripped down version of initial LIGO. It would be a room temperature instrument with fused silicon mirrors like initial LIGO has. The point of that is to build something that does something to demonstrate to the government that something can be built with this stimulus money relatively quickly. And then a second phase would come in where the laser would be replaced with a higher power laser, cryogenics would be installed, the mirrors would be replaced by something more appropriate to the higher laser power and to the cryogenic system. And that would be the second phase. The plan was for the first phase to be operating in about 4 years, maybe 2014 or so. The cryogenic upgrade completed in 2017. I think I forgot a slide with LIGO Australia, but if something happens if LIGO Australia happens, the time it might come online is something like 2017. Because of the time it will take to develop the site, build a vacuum system, install the advanced LIGO hardware, commission it, and so on. So LIGO Australia and LCGT are on similar timescales, several years behind LIGO Australia and Advanced Virgo. Behind Advanced LIGO and Advanced Virgo. So this is a sort of a cartoon of the Kamioka mine. You can see a number of things here. Let's see. above my finger, I can't reach it, is Super Kamiokande, CAMLAND, the neutrino experiments. You see something up here, it says CLEO. That's a prototype cryogenic device that our Australian colleagues have been operating underground. And then this big guy here is LCGT. So you see its scale compared to the other instruments underground there. For those of you who don't know where Kamioka is, it's on the sort of western part. Oh, there's a map here. So the western part of central Australia, of the north-south central Japan. One of the questions people ask is, if LIGO Australia happens, is LCGT redundant in terms of pointing accuracy and things? And of course it's not. I guess conceptually what LIGO Australia does, being in the southern hemisphere, is to improve the sort of north-south location on the sky. LCGT in the northern hemisphere would improve the east-west location. So if you have them both, they both help sort of in a perpendicular way. So this is that same slide that shows the fraction of the sky against the square degree pointing accuracy. And there's about 5 different plots. The red one is just LIGO and Virgo, advanced LIGO and advanced Virgo. Let's see. The blue plot here is like the one I showed you before, which is just LIGO Australia in addition to advanced Virgo and advanced LIGO. The green is not having an instrument in Australia, but having LCGT. And so you see it, in terms of this plot, it gives about the same improvement. And if you have all of them, if you have advanced Virgo, advanced LIGO, LIGO Australia, and LCGT, you get this plot here. And you can see something like 60% of the sky gives resolution under 1 square degree. So that's, yes? Fully operational. These are all for the, the advanced instruments at their design goals. So this is the long, the best we want to do. Okay, so status of LCGT. And the first bullets were before the earthquake. The LCG team is small. They've been looking for help from the rest of the international gravitational wave community. They've talked with us at LIGO. We are trying to help them in various ways we can with design documents, some people visiting, encouragement for Japanese students, postdocs, scientists to come here and work with us on advanced LIGO and learn things. We've even offered them the initial LIGO mirrors for them to use in the first phase if they want. So there's an ongoing cooperation between us and them. The real limitation is that we can't do anything cooperatively that has a negative effect on advanced LIGO. So there's a real limitation of the number of people who can visit and so on. But we're doing what we can. We have an MOU now that includes the fact that in the long run, LCGT would join this international data sharing network if and when it comes online. And the LCGT folks are also looking for help from the other groups in the LIGO Scientific Collaboration, Virgo, and other people. So they're working on the design. They're about to start in the construction. But of course, the earthquake happened in Japan, and we haven't heard yet what impact that will have. But I said funding may be in jeopardy. I mean, I'm really concerned that a project that is just starting out will continue to be funded in an environment where so much Japanese wealth is going to be needed to deal with the disasters, and where I know in high energy nuclear physics, some of their big facilities have been damaged. And I can see that, I can imagine that being a higher priority for some of the science funds. So we don't know what's going to happen with LCGT. We hope that it will happen, but with the earthquake, it may be a new world, so we just don't know yet. There's also news from India. The gravitational wave community in India, which has mostly been theory up to recently, there's a growing interest in expanding the gravitational wave experimental effort, providing ways students can get into the field and so on. And that's resulted in a big step last September when there was approval for a 3 meter gravitational wave interferometer, a lab scale device to learn how to do this stuff, to be funded at the Tata Institute in Mumbai. That's seen as the first step of increasing size and capability in India. They start off with factors, you can see the factors of 10, 3 meter, 30 meter, 300 meter, and then maybe eventually a full-scale interferometer. So that's the sort of longer range picture for the Indian community, but the Indian community also wishes to be part of LIGO Australia. It's a natural that the two countries are relatively close together. There are strong trading relationships between India and Australia, and so it would be a good thing. And there's now been discussions, even meetings and a pre-proposal within India to seek formal Indian joining LIGO Australia, contributing in kind things worth the order of $25 million. There were meetings in February with government officials to explore this, says the proposal is being developed. What we hope happens, it would be great if it happened, would be if India, it's chicken and egg of course, but if India can give signals of being interested in doing this, signals that are taken seriously in Australia, the fact that this is a major trading partner for Australia may help encourage the Australian government to go ahead with LIGO Australia. So this is one of the things we are trying to do to try to increase the odds of this funding happening in Australia. The other thing that's very nice about this, of course, is just seeing a whole new community in India, people who've been involved but really looking ahead and wanting things to grow in this field in India, wanting to see the young scientists have more opportunities in this field. People are coming to visit us now. So this is a plus either way. So, so I think this is my last slide. LIGO is working, and we're working hard to further all these efforts around the globe, because in the end, our scientific interest is to do with our colleagues gravitational wave astronomy, and that needs this globe-spanning network. And so we're working very hard to try to make that happen. Of course, this is not just to look at gravitational wave signals, but it's to provide our colleagues who use other instruments for observation and are interested in following up on these signals to do so. I can imagine when the day comes, we will be sending out telegrams that say, look there. And there could be follow-ups, throughout the electromagnetic spectrum, with neutrino observatories, anything of that sort. The timescale of this, the first part is pretty clear. Advanced LIGO and advanced Virgo hopefully will be on the air at some good sensitivity, 2015 or so. If all goes well, which right now doesn't look really like all is going well, but if it does, LIGO Australia and the Japanese instrument could be online around 2017 or 18. And so sometime towards the end of this decade, there's some chance that we will have this global instrument and be doing that high-quality gravitational wave astronomy. The last bullet is something I added, and it says nature may not be cooperating. There's the earthquake in Japan, there's the floods in Australia. Somehow right now, nature's cards are against us, but we will we'll keep working on this, and hopefully some good things will happen in the next few months. So I'm happy to take questions. Yes.
Are they vacuum system?
They are. There are companies that have built big pipes for industrial purposes, and there have been some interactions with them and with our Australian colleagues, and they seem like they can do it. Tree?
China?
Right. Right. We've explored interest in China. Sri says if China were involved, that would be great. I mean, they are Australia's major trading partner. and so on. There are not too many very strong gravitational wave groups in China, and if something's to happen there, you need very credible people. I've heard that if there's, I mean, what China is interested in doing is promoting their space program, and if there's real interest there in gravitational waves, they would be more interested in sort of the LISA realm. So I don't think it's, at least in this next N years, that's a realistic possibility of having China be involved in this. It's a pity, because that would be a great political match, not scientific. But I don't think that's in the cards.
So along the same lines.
Right. 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 I mean, the places we have, we've looked at India, and we're making some success there. For several years, we've talked to the Japanese about, wouldn't you rather join LIGO Australia instead of doing LCGT, especially in the days when their proposals were being turned down, but that didn't go very far. And so that leaves, Korea, Taiwan, and so on.
Yeah, so you beat the post
Right. Right. And if those nations were to put in some money, in addition to the money, just their involvement would carry a lot of weight. So, but we can just start doing that. There's now a Korean group that's joined the LIGO Scientific Collaboration, so there might be the beginnings of some of those connections. Other questions? Eric? Odds?
Your odds,
right.
Australian that you did.
Oh. When this whole thing, this is worth a little history. When this whole thing came up, I got together, a bunch of, you were included, a bunch of people at LIGO Lab who were senior people. We talked about this. I asked what people thought the odds were. This was a year ago, December, if I remember. And at that point, my odds were the highest. I was the optimist. I said 10%. When we got this approval from the NSF, things were looking a lot better. I was up to 50%, but remember, I'm the optimist. Where am I now? The word I'd use is slim. But I'm at least back to 10%. But I've been the optimist all along. And the thing that, aside from the cost and the economy and the natural disasters, the big problem is the very short time scale. We have to make something happen. We have a very narrow window. I'm not a billionaire, so you can tell that when I try to bet on when I bet on what I think the odds are, I don't do very well. So that's a reason to be optimistic.
It's not a science generated. Sometimes.
Yeah.
Not a lot of examples.
If you could, we haven't done that. The fantasy is if you could excite, Paul Allen put a lot of money into the Allen array. Bill Gates, that's always the fantasy. If you could really excite somebody like that. We haven't. I don't know how to do it. What was the idea? I didn't hear what you said. Who?
Just ask.
Just ask them, right. It's the trouble of finding out which door to knock on. So that's something we haven't pursued. Anybody? Any other questions? Okay.